Yeah, so this is homework 4 for Team Station for the capillary rise in a rough cylindrical tube homework. So for the first part of the first question, we decided to start by doing the energy balance as it asked. So because of this, we looked at the total energy in the system and we broke it into three different parts. We looked at the gravitational energy, the energy from surface tension, and the energy from kinetic energy. So for the energy due to gravity, that's just mass times gravity times height, or in this case, z. The kinetic energy is just mass times velocity squared. And for the surface tension, we kind of ended up having to use a slightly different equation. Because while the first two are kind of obvious and which they can like physics too, the one for surface tension is a little more in depth. So for this, we looked at the area times inhibition factor, where the inhibition factor is the relationship between the surface energy of a dry and wet surface. So in this case, the SV value is for the solid vapor where it's dry, and the LV is for when it's wet. So in this case, you can actually simplify it down to the value for the liquid for when it's wet times cosine of theta. So using this, we can then times this value by the area, which we can calculate as 2 pi RZ. So because of this, we can then plug this back into the total energy equation we had earlier. So now we have mgz minus 2 pi RZ times the value for when it's wet times cosine of theta. But then we ended up deciding that mgz is not really a great way to work at this. And instead, we were going to look at the potential energy due to gravity in terms of hydrostatic pressure times the area. So the way we did that, we had to have that area and we had to integrate it between 0 and z. So when you do that, it's a fairly simple integration, but you do first have to plug in the actual area, which is going to be pi times radius squared. And then when you integrate it, you get pi times radius squared times the density times gravity times z squared over 2. And then now that we had all of these things, which you can then plug back into the total energy equation, we then looked at it when dE dz is 0, when z is equal to h, which is just the max height. And so then doing this, you end up getting 0 equals pi times radius times density times gravity times height minus 2 pi r, the value for what is liquid, times cosine of theta. And if you solve for this, you end up getting Dern's law. So after we did this and we kind of realized that, hey, this is the go-to thing that it should be, we figured we can go on and try to apply this to a rough surface.
Yeah, so now applying that same methodology to a rough surface, we're looking at the area that would be calculated for a rough wall. And what we do is we set a differential element to include both orientations of the angled rough surface. We can use a cosine of the phi angle to relate the normal distance and then the slanted surface distance. And then plugging that into the general equation to solve for surface area, we get, instead of 2 pi RL, we end up having that divided by cosine phi. Then we plug it back into the original equations that we had prior to, and we end up getting something that looks similar to Jordan's law, except now we have the same equation but divided by cosine of phi.
So in terms of force balance, we use this relation, which represents the surface energy of wet and dry surface. We do a simple summation of forces, which is the gravitational force and surface force, and we get to this part, the first equation, the last equation on the left side, which is for the smooth surface. For the rough surface, we have two scenarios from the zigzag pattern, and the only difference here should be the angle theta E1, which is the total angle when we take in account the phi as well. So basically, it's a similar addition of forces. Instead, now the angle we have is 90 plus phi plus theta for case 1, 90 minus phi plus theta for case 2. Because in case 1, the angles are adding up, while in case 2, phi is in the opposite direction from theta. And finally, if the sum and difference of the angle is between 90 and minus 90, we end up with cos theta plus phi equals to cos theta minus phi. We reach this point using some trigonometric identities. And finally, if we do the summation of forces, we get to our equation for the height for the rough surface, where we can see the only difference between this and smooth surface is the angle phi, which is taken into account as plus minus phi.
And now we're looking at the last case in the homework where we have a capillary tube that's been removed slowly from the fluid reservoir. So we can assume that we have a quasi-static situation and the velocity and velocity gradients are nearly zero. If we look at the diagram here, we have three major forces occurring on the column of liquid trapped in the capillary tube. we have two surface tensions, one acting upwards and one acting downwards, and then the gravity acting on the liquid. So because the liquid is trapped, we assume that there are going to be two different contact angles, one being theta 1 and the other being theta 2. And if we go through the derivation, we find that the height at the end at the static location is going to be just using the same thing as Jordan's law, but accounting for the difference in the contact angles as well as the roughness angle phi.
Now, since these equations are supposed to be the same, they should converge at phi equals 0. For equation 1 and equation 2, obviously this is pretty straightforward. You just plug in phi equals 0 and you get a nice explanation of Jordan's law right there for those two. Now for the third one, obviously since we have two different contact angles here, it's not actually going to be the same as that, unless of course theta 2 is equal to 0 as well. But mostly they do converge at 0. Now here we actually plotted the equations to make sure that they were sort of equivalent while we're going through them. This is actually where we ran into a slight problem, as you can see on the plot here. One of them goes to about 0.85 meters when the contact angle is negative 89 and 89 degrees, whereas the other approaches 0 meters. Now they do converge at 0 still, so that does check out at the very least. For this, we assumed a 0 degree contact angle, so theta is equal to 0 and a radius of 1 millimeter, which was just chosen arbitrarily. Again, the plots are dissimilar to each other since one of them does tend to go up as the phi angle decreases and increases past 0, and the other tends to go to 0. But they are symmetric about phi equals 0, so that does sort of act as a sanity check for us, because if you think about the dimensions of the tube itself, if you have that phi angle going inwards or a negative phi angle or outwards, you're approximately making the same shape. So it should be symmetric at the very least. And here are our citations.